Good afternoon to everybody. Once again, myself Chintan, and welcome you all to this Vyom webinar on Observational and Theoretical Astronomy, which is jointly organized by Astronomica, Astronomy Club of St. Xavier's College, Ahmedabad, and Department of Physics and Electronics, St. Xavier's College, in association with Essencetech. Now, I welcome you all in this very first lecture by Dr. Vishal Joshi, sir, Astronomy and Astrophysics Division, Physical Research Lab. Now, before starting that, I would like to invite Dr. Rajesh, sir, the head of the Department of Physics and Electronics Department, St. Xavier's College, for their opening remarks and you to brief about this Vyom. Please, sir.
Rajesh Bhai. Hello.
Electronics Department
Yes, sir.
of St. Xavier's College, Ahmedabad. I would like to extend a very warm welcome to all of you and hope all of you are very safe in these trying times of COVID-19, which has engulfed the entire world. I'd like to give you a brief information about the Astronomy Club, which has been instrumental in organizing this event, along with other associate partners. It all started about 7 to 8 years back when our our ex-principal, Father Vincent Briganza, gifted us one telescope. Now, this telescope was then used by the Astronomy Club for stargazing, watching planets, astronomical events such as Venus transit, solar eclipse, lunar eclipse. All these events were viewed by the telescope. This generated a lot of interest amongst the students. And this particular webinar is a result of that enthusiasm which has grown out of this club. And as a result of this, we also introduced this in our curriculum, in our postgraduate courses. We have been very fortunate to have excellent resource person who have been guiding us. Two of them are resource person in this webinar. I'd like to especially thank Professor Vishal Joshi and Professor UC Joshi of PRL Ahmedabad, and also Dr. Professor Brij Mohan Thakur of SP University. This club comes under the flagship program called Physics for Tomorrow, which caters to various co-curricular activities amongst the students, such as research projects, participating in seminars, conferences, competition of quiz, experimental physics, computational physics, and many such activities, which has generated a lot of interest in the field of physics. And I would like to welcome once again all of you and extend a very warm invitation to all of you. If you come to Ahmedabad, do visit our college. Enjoy this webinar. Thank you.
Thank you so much, Rajesh, sir. Now, after this, I would like to invite Dr. Tushar Pandya, sir, for the brief introduction of the today's speaker. Yes, sir.
Thank you, Rajesh Bhai, for your kind words. Dear students and physics educators, it gives me great pleasure to introduce an expert and our friend Dr. Vishal Joshi. He is currently working as a scientist in Astronomy and Astrophysics Division, a physical research laboratory, and he has been working in the field of astronomy and astrophysics for over 12 years. Dear friend, during his research career, he has significant contribution to the understanding of various physical, orbital, and geometrical aspects occurring on and around novae, supernovae, and other variable stars using ground and space-based observation models, simulations, and theory. Dear friends, after getting master degree with gold medal in physics from Saurashtra University in 2005, Dr. Vishal Joshi joined PRL as a research scholar. He completed his PhD on observational study of magnetic variable star. He won postdoctoral fellowship awarded at the prestigious institute Inter-University Center for Astronomy and Astrophysics, which we can say IUCA at Pune, where he obtained a valuable experience in the field of astronomical instrumentation. He joined PRL as a scientist from January 2016. Dear friend, he has published more than 30 research papers in a very reputed international journal. And I'm very happy to inform you that one of his research papers is published in Nature, the most prestigious journal in scientific research. Vishal bhai, congratulations for your great achievement.
Thank you. Thank you.
He uses many telescopes like Mount Abu Infrared Telescope, Himalayan Chandran Telescope, European Very Large Telescope, Infrared Telescope, and the facility in USA and Hubble Space Telescope for his research. He has significantly contributed towards the computational astrophysics and automation of data analytics. He has prepared automated data analysis pipelines for several instruments used worldwide. Friends, he is currently working on the project to commission 2.5 meter class telescope at Mount Abu Observatory, which is going to be the second largest telescope of India. He is a member of International Astronomical Union, Indian National Science Academy, Gujarat Science Academy. Friends, he is also very nice in science popularization. He has delivered more than 150 popular lectures and conducted more than 50 workshops and various scientific topics on astronomy, physics, and mathematics across the country. He is associated as an advisor and resource person with Science City, Regional Science Center of Rajkot, Narmada Nagar Community Science Center, Vignani. Dear friends, really we are fortunate that we are with an expert online. So with this brief introduction, I would like to invite Vishal Joshi for his presentation on Twinkle, Twinkle, Oh Big Stars. Sir, thank you very much for accepting our invitation and being with us. And over to you, sir. Thank you.
Yeah. Thank you. Thank you for inviting me and giving me an opportunity to interact with all these young minds, ignited minds of our country. I thank St. Xavier's College and Astronomica Club for this opportunity. Since this is the first lecture of the series, and I came to know that the audience is of broad spectrum from wide range, I decided to make my presentation as popular as possible. So I'll try to bring it to the lowest and interesting most possible level. Still, keep noting your questions. We will have a question answer session immediately after the presentation, and we can discuss all your curiosities after the presentation. So I'll start my presentation.
Please proceed, sir. Please proceed.
Pardon?
Yes, sir. No problem.
Yeah, okay. So I'll start with focusing on this part, astronomy and astrophysics. Frequently students ask me, what is the difference between astronomy and astrophysics? So let me start with this part, and then we will continue our journey to the universe. The difference between astronomy and astrophysics is like, astronomy is the study of universe beyond Earth's atmosphere. The main branches are astrometry, celestial mechanics, and astrophysics. So astronomy is a wider domain in which the astrophysics is a subdomain of astronomy. But I put this way, that astronomy is any kind of study of any celestial object, starting from hundreds of kilometers above the surface of the earth till end of the universe, if it is. And astrophysics is a specific branch which focuses not only the fundamental study, but also focuses on the physical processes happening in all the celestial objects across the universe. Or in other words, I would say that astrophysics is the application of physics in celestial objects. So basically, astrophysics is a science in which nature has given us the laboratory. So our laboratory is available with us. Nature has designed our laboratory. We are studying all the celestial objects, starting from our sun, planets, comets, asteroids to stars, planets around the other stars called exoplanets, and extragalactic objects like other galaxies, quasars, and all these objects. So astrophysics needs physics. We need to have the fundamental physics understanding to apply in the astronomical observations. But occasionally it goes otherwise also. Our astronomical observations gives us insight to understand, to develop physical principles, physical laws, which are, yet unknown to us. With this, I will focus on this plot. In general, I keep minimal number of plots in my popular talks, but this plot I feel is essential. Without this plot, without this figure, nobody can start understanding astrophysics. One can understand astronomy, but not astrophysics. So this plot is basically a simple plot where the x-axis you can see is the surface temperature of the stars. So the star has a surface temperature, and y-axis is luminosity. Luminosity is kind of the amount of light emitted by the star. So if you take a star, measure the temperature of its surface and also measure the total light emitted by the star, and you put these two numbers as a point in this graph. Take other star, I calculate, estimate these two quantities and put another dot, and if you keep putting several dots, several hundreds of dots, several thousands, millions or billions of dots, you will see a pattern. And this is a really surprising result. This was surprising result, and this is surprising result for new students in astrophysics. See, we expected the temperature of the star and the total light emitted by the stars should not have any strict relation. Any star can have any temperature and it can emit any amount of luminosity depending on its size and all. But in early 20s, two scientists, Hertzsprung and Russell, have realized that no, few fundamental parameters of stars like its surface temperature, its size, and its mass are tightly connected to each other. If you know one or two parameters, you can estimate about the other parameter. So here, if you focus, let us try to understand this plot. This plot says, before explaining this plot, I like to highlight one interesting thing. Usually, our x-axis has zero value at origin and has larger values. The values keep increasing in the right hand side. Here the plot is otherwise. If you notice it, at the right hand side temperature is less, at the left hand side temperature is high. This is opposite to our convention. but there is some reason for that. I will probably explain after some time. But right now, keep in mind that the point falling in this zone, rightmost zone of this plot, are cool stars, whereas the points falling in the leftmost zone are the hot stars. So you can see that in our universe, the stars which are very hot are emitting huge amount of light, And whereas the stars which are cool are emitting less amount of light. And as you know, as a physics student, you know that the temperature, surface temperature of the star is directly connected to its color also. Hotter the star, bluish white its color is. Cooler the star, it appears red, orange or red color. So you can see the various color range of the stars also here. At the same time, the size of the stars are also tried to highlight here. You can see hot stars are much bigger in size compared to cool star. Please keep in mind that the sizes of the stars are not in scale. The scaled picture I am going to show you, and you will realize that I cannot put the scaled picture here in this graph. This graph size is not sufficient enough. The stars are so diverse in their size, temperature, luminosity, densities, and other various parameters. Focus in this line, this strict line. See, you can find stars everywhere across this plot, but this specific line is, eye-catching. This line is called main sequence stars, and the stars falling on this line are called living stars. Most of the stars available in our universe are falling in this zone. The stars are, producing energy because of some nuclear processes called fusion processes. Primarily, in the core of the star, 4 hydrogen fuses to produce 1 helium nucleus, and in this process, star emits the light. This process keeps star in life. The star will not collapse under its own gravitation because of this process. And in this, when the process is going on, the stars are within this strip. The stars are within this strip. Once this process stops, star will go to the death process. And in that process, star will leave this line, and its luminosity, its temperature changes such that star will move to other places of this diagram. Pardon me if you find this little confusing. Some of you are physics students, will find it interesting. Some of you may not be physics students, but with time you will appreciate this graph. With this, I'll start introducing various type of stars to you and their wonderful properties. The first part is the size of the star. You can see that the stars has diverse sizes. Forget this character, these alphabets M, K, G, F, A, B, O. Focus on their color and their size. The hottest stars are largest in size, and they are also most luminous, whereas the coolest stars are smallest in their size and also less luminous. Similarly, their masses are also diverse. Hottest main sequence stars are so heavy that its mass falls maybe 50, 60, 70 or 80 times solar mass of the sun. So single star can be as heavy as 50 to 80 suns, whereas the cooler stars are barely 10th of the solar mass, barely 10% of the solar mass. So mass, size and all are highly diverse. Our sun falls somewhere here. It's moderate in size, neither too small nor too big. It's moderate in shape, moderate in mass, neither too heavy nor too massive, and it's moderate in luminosity also. So our sun is a very ordinary middle type star, not falling in any extreme. Coming back, I'll show you the position of our sun. You can see sun is around here in this part. I hope you can see my cursor. Someone please confirm that you people can see my cursor.
Yes, sir, it is visible.
Okay, great. So sun is here. I think I can take a lesser pointer. So sun is here. Now let me introduce sun. Sun is the nearest star. Sun is the star we can study in greatest detail. Rest of the stars are too far from us compared to sun. Till a decade back, we could not observe a single star except sun in resolved manner. We could see some stars are so faint that we can see stars as a point-like object only. But a few techniques have been developed called adaptive optics and interferometric techniques. Now we can start resolving some of the biggest stars. So sun is probably the only star we can resolve it in great detail. So it is better to take this opportunity and understand the processes occurring on the sun. Many of the processes occurs on other stars also. So let us understand our own star, our sun, before moving to other stars. If I ask even an BSc or MSc physics student that give me 10 scientific facts of the sun, usually I don't get it because we barely know anything about the sun. We know that yes, sun is very bright, hot gas of ball. It's ball of gas, and we also know that sun has some dark regions called sunspots. But if we look into the detail, if we zoom this sunspot part, it gives us very interesting information. Some hundreds of years back, 300, 400, 500 years back, Galileo observed sun in great detail. He first time observed, identified and discovered the sunspots, and tracing those sunspots, Galileo estimated the rotation of the sun. And to his and to our surprise, Galileo found that sun rotates at different speeds. Unlike Earth, if you take any point near equator or near pole on the Earth, the rotation period is always 24 hours because Earth is a solid body. In case of sun, the region near equator rotates much faster. It completes one rotation in 25 days, whereas region near poles completes rotation in 35 days at very slow pace. This shows that sun is actually made up of gas. Sun is not solid surface. If sun is not solid surface, how can I use the word surface of the sun? Now this is interesting. Many of the time we use surface of the sun or surface of the star, but actually there is nothing like hard surface on the sun where you can actually stand. Forget the temperature. Even if sun is cooler star, you cannot get any hard surface on the sun. In fact, the word we use surface of the sun or the surface we see on the sun is actually much thinner than our own atmosphere. It is barely 0.05% dense of our atmosphere. So this is interesting fact. Sun has no hard surface. It is totally made up of gas, and the surface we see, the layer we see is very thinner than our atmosphere also. Let us zoom in the sunspot, and you can see the sunspot has a detailed structure. The core of the sunspot is dark, whereas the boundary of the sunspot called penumbra is fibrous. And even the region around the sunspot and region across the sun surface is actually granular. They are not smooth, they are granular. This granular surface is primarily because of the convection occurring within the suns. This convection is very much like convection occurring in our own atmosphere or the convection in a boiling water bowl. The same convection. Also, sun shows the number of sunspots and other solar activities changing with time. Sometimes you see sun is very passive, very cool, calm-minded, whereas sometimes you see the sun in Durvasa mode, very aggressive, very active, very angry. When people studied the activity of the sun by means of measuring the number of sunspots on the sun as a function of time, you can see here we have the data from 1700 or even before till date. Scientists, astronomers, solar physicists are keep measuring the number of suns on daily basis and they are plotting it. And you can see the number of sunspots on the sun are actually varying. They are increasing, decreasing, increasing, decreasing, increasing, decreasing, and so on. If you measure the periodicity, you will get 11-year periodicity. So every 11 years sun become active and passive. The activity of the sun has some direct and indirect impacts on the earth also. Like, as I told you, we have some data before 1700, from 1600 also. We have noticed that from 1650 till 1700, the number of sunspots were very less. And we also faced, especially high latitude places like European countries and all, have faced mini ice age. The temperature of our earth, our atmosphere went down compared to the normal temperature. We were facing mini ice age. Similar low sunspot period fall from 1790 till 1830. And in this phase also, we have observed the atmospheric temperature has fallen down. These two periods are known as Maunder minimum and Sporer minimum. Coming to the sunspot, how this sunspot forms? What causes this sunspot to generate on the surface of the sun? That is magnetic field. You know, our Earth's magnetic field is very systematic and symmetric and long-term stable. We know that our Earth's magnetic field is dipolar in structure, whereas sun has no large-scale systematic structured magnetic field. Sun has a local magnetic field. However, this local magnetic field is extremely strong. The strong local magnetic field forms this sunspot. So magnetic field lines are coming out of the surface of the sun and goes in again in the surface of the sun. These foot points of this magnetic field lines form sunspot. And this is not simply hypothesis. We have real pictures. We cannot see magnetic field lines in any case. We cannot see magnetic field lines. But if something is aligned on that magnetic field lines, we can see that material. Here on the surface of the sun, the plasma of the sun align on these magnetic field lines. This plasma are hot, bright, and so we can see this plasma aligning on the magnetic field. You can see loop-like structures. This individual loop-like structure represents magnetic field lines. So sun has strong magnetic field in loop structures, and that produces sunspot. This is another beautiful picture. These pictures are real pictures captured by a satellite called TRACE, T-R-A-C-E, TRACE. Also, sun is emitting huge amount of mass and energy. The mass is emitted in terms of solar flares and coronal mass ejection. The sun has its own atmosphere also. which has the name corona. Please, the atmosphere of the sun, corona, has nothing to do with non-virus corona. We are facing the problem in these days. So this solar corona, the atmosphere of the sun, is also keep emitting gases and plasma along with huge amount of energy. You can see a cloud is bursting from the surface of the sun, and you can see the size of this cloud compared to the earth. So such clouds are 1,000 times, tens of hundreds of thousand times larger than the earth. Of course, their densities are very low, so masses are not as high as earth, but size is definitely. I'll show you a video in which I'll show you the unzoomed picture of a specific region of the sun. You can see a bright region here. You will see a burst occur in this region and see the same burst at zoomed out version. I hope you will be able to see this video. Please somebody confirm that you can see this video.
Yes, sir, we are able to see.
You are able to see. Okay. Similarly, as I told you, this atmosphere of the sun is visible here. In order to see the faint atmosphere, we have to cover the sun. You can see a black disk here. This is the disk placed in such a way that it will hide the sun. So it's kind of an artificial solar eclipse. When you hide the sun, you can see the atmosphere of the sun. So it is radially outward moving structure and extended to large size. The inner circle, white circle, represents the size of the sun. You can see how extended is solar atmosphere. And the mass coming from the sun and solar corona sometimes comes to the earth. They cannot penetrate Earth's magnetic field. So they will go along the magnetic field lines, goes near the polar region and forms the beautiful structure called aurora. In the north or south polar region, if you visit places like Norway or Greenland, you can see occasionally this kind of beautiful, colorful, sky show in the night time, and this is called aurora. This color, this light emitted by the interaction of solar particle with our atmospheric particles. And solar atmosphere extends not only to Earth, it extends to other outer planets also, like Jupiter. And this solar atmosphere, the solar mass, solar material, plasma, interacts with Jupiter or Saturn's magnetic field and produces aurora there too. So aurora is not occurring only on Earth, they occur on other planets also. This is another interesting fact I find. This is another example of aurora occurring on the pole of Jupiter. This picture is captured by Hubble Space Telescope. Coming back to the HR diagram again. Since I have shown you the physical processes occurring on the sun, anyway, what I have explained is just a glimpse of sun. If we want to understand the sun in detail, we need whole day workshop or maybe even longer time, because sun is a wonderful object to know. We yet not understand sun even up to a few percent also. Sun is still hiding many interesting aspects. But here from sun we will move to hotter stars and later to cooler stars and see how they are differing from the sun. Let us focus now on these cooler stars. They are called red dwarfs. So red dwarfs are the stars which are low in temperature. You can see that its temperature is barely 3000 degrees Celsius or Kelvin. Typically in science we use the term Kelvin. So cool stars are really cool. The surface temperature of sun is around 6000 degrees Celsius, 5800 Kelvin, whereas the cool stars are little more than half of this temperature. At the same time, their size and their mass are also less than half of the sun. So the stars are really small, they are cool. And in universe has a life cycle. The stars have their life cycle. And the lifetime of the star inversely proportional to its mass. Bigger the star, less the time it will spend in life in main sequence. The smaller the mass, the life will be larger. I usually compare it with a sumo pahalwan and an ordinary healthy lean person. A sumo pahalwan is very massive but does not live long. The average age of sumo pahalwan is barely 40 to 50 years, whereas ordinary healthy living person has much larger life, maybe 60, 70 or now 80 years. Here I have shown the same part in plot. You can see even in case of low masses, if the mass is higher, the mass is in terms of solar mass. So if the mass of the star is barely 25% of solar mass, its life is about 1 trillion year. 1 trillion year, remember, 1 trillion year. 9 zeros after a 1 is called 1 trillion year. Whereas sorry, not 9, it's in fact 12 zeros. Whereas if the star is less in mass, maybe barely 10% or even less in mass, the life is much higher, 10 trillion years or higher. Now compare these numbers, trillions of years, with the age of the universe. We today know that the age of the universe, the time spent after the Big Bang, is 13.6 billion years roughly. That means the age of these cool stars are much larger than the age of the universe itself. That means the star has formed in the universe as a cool star has never seen its death. We cannot see the death process of any cool star, because the lifespan of the cool star is much higher than the life of the universe itself. And still we are trying to predict the death processes of these cool stars using the non-physics. We try to apply the non-physics to the structure of the star and try to understand how the star will go to the death process at the end. So this is the fun in science. You do not need to observe each and everything. You observe one or two things, apply your non-knowledge and try to understand the things or the processes you have not observed also. I usually give one interesting example that if you know that Mahesh and Suresh, two person, are brother-in-laws of each other. वो एक दूसरे के साले बहनोई है. So you are given information of two persons only, but you immediately know that there should be a lady between them who is sister of one person and wife of other person. So you are given information of only two persons, but from your common sense you can infer, you can feel the presence of the third person also. So science works like that. You observe something, apply your understanding and extend your knowledge, your understanding. Okay, so leaving these cool stars, let us move to the hot star also. Before this, I will explain some other properties of these cool stars also. As I told, they are small in size, mass, and their luminosities are also very low. Since their luminosities are very low, the light emitted by the stars are very low, they are difficult to detect. Now, there is a paradox here. Can you believe these cool stars are most in number in our universe? The basic estimation says that almost 70 to 80% of the total stars are cool stars. So these stars are, high in number in universe, and yet we have detected few hundreds of such stars only, few hundreds to few thousands of such stars only. The extreme cool stars I am talking about. We know say millions of such cool stars, but we cannot detect each and every star. The reason being their low luminosity. Since their luminosity is low, we can only take picture of the stars which are close to us. We cannot see the stars very far from us because their luminosity is too low to see. They are long-living stars, and their atmosphere is rich in atoms and molecules. Now this is interesting. Solar atmosphere has almost no atom. The surface of the sun, the temperature of the surface of the sun and the temperature of the atmosphere of the sun, corona, not allowing molecules to form, even atoms to form. The surface temperature of the sun, as I told, is 6,000 degrees Celsius. Surprisingly, the atmosphere of the sun, the corona, has much higher temperature, much higher temperature. The temperature of the corona is 1,000,000 temperature. Now, this is surprising. It's like the bowl kept on the gas stove has more temperature than the flame itself. Can it be possible? Can the bowl has more temperature than the gas flame itself? It cannot be. And so we cannot expect corona to be very hot. But this is fact, we have measured it, and this is still open problem for astrophysics or physics in general. We don't know the real reason. We have some estimates, we have some guesses for this coronal heating problem, but we yet don't know 100% with confidence that why corona is so hot. Such high corona is not allowing atoms to form even. So corona is made up of ions only. But in these cool stars, the atmospheres are also cool, and they allow atoms to form, even molecules to form, even clouds to form. We have some direct observational evidences that such cool stars have clouds in their atmosphere. So the clouds are not only available in planets, they may also present in stellar atmosphere also, if the star is cool star. As I told you, the cool stars are rich in number in the universe. I'm giving you one beautiful example, Proxima Centauri, the nearest star from our solar system. Proxima Centauri is actually a cool star. Rather, it is pair of cool stars. It is a binary star made up of two cool stars orbiting around each other. Moving ahead, leaving the cool stars and moving to the hot stars. Anyway, I will come back to the cool stars, or I would say cooler star. But let us focus now on hot star. As I've shown you, the hot stars are much, much larger in size. They are very big. Their sizes are tens of the solar radii. And in volume, they are 1,000 times bigger than sun. They are very hot also. Their surface area is more. Their temperature is more. The temperature of its hot stars are from 10,000 degrees Celsius or 10,000 Kelvin to say 35,000 degrees Celsius or even more. So they are extremely hot, extremely big, and so their luminosities are very high. Such high luminosity stars should be easily visible, and yet we have observed not many such hot stars. The reason being, these hot stars are not in big numbers in our universe. See, in universe, cooler stars are more in number. As you find the hotter star, their number densities are less, their numbers are less. So you will find cooler star very easily, but you cannot find hot stars. So the extreme hot stars are few hundreds of such stars are known. We know few thousand to few million to few billion intermediate mass, size, and temperature stars, and we know that the cool stars are of the number of few billions or even more. So these stars are big. Their surface temperature is so hot that the radiation emitted from that surface is actually has so high pressure that it will push away the atmosphere of the star itself. The material of the star is pushed away by the radiation itself through its radiation pressure, and that's why these hot stars are known to emit huge amount of mass in the space. They are throwing huge amount of mass in uniform manner in the space, and such high amount of mass is visible occasionally as a nebula. I am showing you two beautiful examples called Trepide Nebula and NGC 6826. Not all these nebulae material are thrown away from the star. Most of these materials are actually present before the sun, before the star. Rather, I can say that stars are made up from some of this material only. And then star is actually adding back its mass to this nebulae. The star is radiating, and the radiation is actually, scattered by the nebulae, and so we can see this nebulae glowing. So this is an example of Trepide Nebula, and the central bright star you can see here is actually glowing this nebula. This is another example where you can see the material actually thrown away by the star. You can see that they are symmetric in shape, and they are in two layers. These two layers represent that the star has thrown away huge amount of mass in one episode first, and after some time it has thrown the material in second episode also. So the stars are continuously throwing mass, as well as they are throwing mass in episodes also. And this thrown material can be seen thanks to the radiation of the star. You can see two red colored structures also here. So there may be jets emitted by the stars also. Jets are also very common. When I say jet is actually the emission of material in very narrow region, narrow conical region. So jets are very common. Jets are there in various physical celestial objects and physical processes. When the star starts forming, jet ejects. When the stars will in dying process, they will again eject the jet. So these are the hot stars, these are the cool stars, and then I am going to introduce even cooler star. We don't know whether we should say them star or not. We knew such objects are there, but they are so small in size, so low in temperature, and hence so less in luminosity, so faint, so dim in luminosity, we didn't capture such objects actually. But in last 2 decades, we have started observing such objects using our high-tech telescopes and cameras. Some 2.5 decades back, maybe around 1994, first such objects have been identified. What are these objects? Let me introduce. So these objects are called brown dwarfs. Don't go to their number. They are not really brown in color. See, we knew the coolest stars were red stars, and then we found some stars which are even cooler than red star. following the convention, people have assigned some color and that color is brown. So this is convention. They are not actually brown in color, but yes, their colors are close to red colors because they are even cooler stars. Are they failed stars? As I informed you initially, the stars will go in main sequence, or star will enter in their life when the hydrogen fusion process starts in their core and continues in their core. So this fusion process, the process which provides energy to the star and then to the universe, should continue in the core of the star. But this process is a tricky process. It requires some stringent conditions. It requires some high temperature and high densities. If the star has not sufficient mass to provide such high temperature and densities, even in the core of that star, the fusion process of hydrogen cannot start. So the stars do not have their own fusion process going on in their core, which provides them the energy. They may have some different fusion processes which require little less temperature and densities, like fusion of deuterium or fusion of lithium. These two materials are also available in the star, not in extreme high densities, but they are there. So in core, in relatively cooler core, this molecule, this ions, lithium or deuterium, can fuse and provide some amount of energy, but not sufficient amount of energy to form them as a star. So these objects are called as brown dwarf. They are actually failed stars. They are not yet, formed as a star. Even our Jupiter is also sometimes considered to be failed star. We know that even the mass of the Jupiter is, say, 100 times larger than this, then it would be a full star. But Jupiter is a planet. Now realize, Jupiter is a planet. The coolest star has mass of about 80 Jupiter. So we have one Jupiter as a planet, we have 80 Jupiter mass as a star, and there is a gap between one Jupiter mass to 80 Jupiter mass. And these brown dwarfs are actually the objects filling this gap. The brown dwarfs has mass from 13 Jupiter mass till 80 Jupiter mass. So they are actually bridging between the stars and planets. They are small in size, mass, and luminosity. As I told you, their masses are barely 1% to 8%. Give me a minute, and I'll explain the consequences of this. Their masses are barely 1% to 8% of solar mass. Their size is small, their mass is so small, even the temperatures are very less. The temperatures are less than 3000 Kelvin, 2000 Kelvin. Sometimes the temperatures are 1000 Kelvin. Sometimes they are even lower. I will come to that part. But there's this low temperature, low size provides them low luminosity. And that's why these brown dwarfs are even difficult to detect. They are very, very difficult to detect. As I told you, in 1994, the first brown dwarf have been detected by 4 scientists working in California Institute of Technology, Caltech, and one of these scientists was Indian origin. His name is Srinivas Kulkarni. Srinivas Kulkarni, popularly in astronomical community, popularly known as Srini. So Srini is yet a big name in astronomical community. He is highly active till date, and he was the one of the discoverer of first brown dwarf. I'm fortunate enough to collaborate with him. We have studied some objects with our facility, with their facilities, and in this joint study, we have published some results also. Now, I told you that these stars are very cool and very low in luminosity. That I am demonstrating here. The left image you can see is captured in very low wavelength light, high energy light. This is basically blue color light. The light around 400 nanometer is used in this image. So stars are emitting virtually complete spectrum, starting from X-ray till radio waves. We put some filters in front of our camera to take picture of particular wavelength range only. So this blue color image of the sky part, you can see no object in this cross region, the central region. You cannot see any object. But the same region, if you see in lower wavelength, say around 2000 nanometer or 20,000 angstrom, this is called near infrared wavelength. You can see a bright enough star, very bright star compared to the nearby field stars. So this star is very bright in infrared, but not bright at all in visible light, and that's why this should be a very cool star. This is an example of brown dwarf. So brown dwarfs are easily detectable in infrared wavelengths, but not easily detectable in optical wavelengths. Now we have many cameras, many spectrographs in optical across the world. I'm not talking about India. I'm talking about the whole worldwide facilities. We have many optical facilities available with us, but we have not so many infrared facilities. One reason was technological reason, because infrared cameras are not easy to deal with, to fabricate with, and to work with. But recent technologies are allowing us to make more and more sophisticated infrared cameras, and so astronomical community is now moving from optical to infrared. Like Hubble Space Telescope had many optical instruments and few infrared telescopes. Now the next generation James Webb Telescope will have more infrared facilities and very few optical facilities. James Webb Telescope will be most likely the complete infrared facility. So infrared astronomy is growing good now. I am an infrared astronomer. I am primarily studying various variable stars and novae and supernovae, primarily in infrared. Also, I am studying them in optical and X-ray regime also, but primarily I'm using. How much time I have? I have 10 more minutes. I hope I will complete in time. So as I told, their masses are smaller than solar mass. Their sizes are comparable to Jupiter mass. And interestingly, unlike other stars, this brown dwarfs has very little variation in their size. Remember, their mass has large variation, almost 800% variation, 1% to 8%, to 8 time variation, 8 time. Whereas here, it is not even double. The minimum smaller white dwarf to larger white dwarf has barely 15% change in their size. And here is a example of that. This is artist impression. All these pictures are not real pictures. They are artist impressions. So don't say that I have shown you the real picture of brown dwarfs. Please, we have no real picture of brown dwarf till date. So this is the sun in scale. This is a particular star close Gliese 229a. It is actually a red dwarf star of temperature 3600 Kelvin. So this is moderate star, this is cooler star, and they have different sizes. But when you enter into even cooler region where white dwarfs falls, these 4 stars are white dwarfs. Sorry, 3 stars are white dwarfs, and this is Jupiter planet. You can see that these 3 white dwarfs has different temperature, even different masses. The TAID one is actually much heavier compared to WISE 1828. It is almost 5 to 6 times heavier than this, but their sizes are almost comparable, even comparable to Jupiter. Why so is an interesting problem. We partially know the answer, and that is because of what we call degeneracy. I'll not explain this process because it is very interesting, but time is not permitting me. So what I wanted to highlight here is their masses has wider range, but interestingly their sizes are not so varying with mass. Going back, they are low in temperature. As I explained here, some white brown dwarf are 2600 Kelvin, whereas we know some brown dwarf which are barely 300 Kelvin. Remember, 300 Kelvin. We know with confidence some brown dwarfs, their temperatures are barely 300 Kelvin. 300 Kelvin corresponds to 27 degrees Celsius, corresponds to room temperature. So we have some brown dwarfs available in the universe which has very low, comparable, rather comfortable temperature. If you want to visit such brown dwarf, you should not worry at least about the temperature. You will find very comfortable temperature. And not only that, recently, in last 1 to 2 years only, we have identified some brown dwarfs. Remember, I'm saying that brown dwarfs are not stars. They are the bridge between planets and stars. So don't say that we have stars of such low temperature. No, we don't have any star of room temperature. But we have star-like objects called brown dwarf of low temperature. In recent couple of years, we have identified few brown dwarfs which has even less temperature. The lowest temperature brown dwarf, the coldest brown dwarf we have identified has temperature between -13 degrees Celsius to -48 degrees Celsius. So they are freezing dwarf. So they are not stars. What I have mentioned here is actually wrong. They are actually refrigerator objects, stellar objects. They are refrigerating brown dwarfs. Like cool stars, they also contain atmosphere, but their atmospheres are full of molecules. See, the cool star also have molecules in their atmosphere, but do not have the wide varieties of molecules, as the temperature is not allowing all the molecules to form because the temperature is still higher compared to white dwarfs. Whereas brown dwarfs, whereas in case of brown dwarfs, you may have water, you may have oxygen, you may have hydrogen molecule, you may have methane molecule, you may have carbon dioxide molecule. Name a molecule and there are chances that they may be there. Space is full of molecules also. Not only this atmosphere of the stars, even the space between the stars are also full of molecules, and we have identified many molecules. Simple molecules. Hello, are you able to hear me?
Yes, sir, audible.
Yes, okay, because I got an indication of poor connectivity. Anyway, so yes. So we have simple molecules like water, methane, carbon monoxide, carbon dioxide, as well as we have complex molecules like long chains of organic and non-organic material. And surprisingly, we have some interesting molecules like fullerene. The fullerene is what we say spherical molecule of a carbon, the football molecule we usually say. This fullerene we have also discovered, we have detected in space also. So such space is, diverse in every sense. Okay. So these are some artists' impression of the cool stars. And now I'll show you that the cool stars, these brown dwarfs, are not isolated all the time. Like other stars, they are in binary also. Let me tell you that almost 90% of the stars, 80 to 90% of the stars in the universe, ordinary stars, are in binary or multiple form. Sun is falling on that exceptional 10% stars which are isolated, they do not have any binary companion. So I usually compare it with our social structure. Most of us are married in our social life, but very few are unmarried. In case of stars also, they always love each other and to marry them. Brown dwarfs are also not exception. I am showing you few examples. The leftmost example, Luhmann 16, is a pair of brown dwarf. Both these star-like objects are brown dwarf. These images are captured in infrared. Remember, we cannot see these stars such bright in optical. So these are infrared images. You can see them moving around each other. We can see them moving around each other because their orbital period is less. So in small time, we can see their motion. These are 4 stars, their orbital periods are larger. So in small time, in few years, we cannot see their complete orbit, but still we can see them moving around each other. So this is the story of the main sequence star, the stars living their ordinary life. But when stars are at the end of their life, they will leave the main sequence. The main sequence is nothing but the combination of temperature and luminosity. So then the temperatures and the luminosities will change so that the star will, move in this plot like this. These are white dwarf. You can say the dead bodies of the stars, of the low mass stars. If the star is high mass star, their dead bodies are either neutron star or maybe black hole or magnetar or like these objects. Anyway, what I have explained are main sequence stars, but remember the star has much larger variety than what I have explained. Almost 97–98% of the stars are not varying in their luminosity. The light coming from the stars are not changing in time, in small time duration. Eventually, their light will eventually change. It will pass through the dying phase. But in small time scale, maybe in few seconds, few minutes, few hours, days, years, or few centuries. In this period, most of the stars in human lifespan, they are invariable in their light. But 2% of the stars are such that they are changing their luminosities. They are changing their luminosities. They are variable, and variable stars have their own zoo. I will not explain this all these type of stars, but I will explain that all these subsections you are seeing are representing different type of star. Many stars are there in one subsections and they have their characteristics. So it's like variable star zoo, like our ordinary zoo. We visit the zoo and we see diversity of animals, creatures. Like here also in universe, we have diversity of variable stars. With this, I will move to some last part of my slide. I will skip some slide as time is not permitting me. I wanted to explain some variable stars, but let me tell you, the nearest stars, Alpha Centauri and Proxima Centauri, they are also binary stars. As I told you, 90% of the stars are binary or multiple star system. Alpha Centauri is 4.37 light years ahead, and it is actually a binary star. It has a companion called Proxima Centauri. The Proxima Centauri is the nearest star to Sun. It is 4.24 light years. And as I told you earlier, in fact, this Proxima Centauri is also a binary star. Proxima Centauri is also a binary star where two cool stars are orbiting around each other. So it is a complex system. Two stars are orbiting around each other, and these two stars are collectively orbiting with the other Alpha Centauri stars. Their orbit is like this. And then I will tell you that Proxima Centauri is the nearest star today, but it will not be the nearest star all the time. I'm showing you a plot in terms of time from minus 20,000 years to 80,000 years. And here is the distance of the various stars from Sun. You can see Proxima Centauri, this yellow line, is closest to Sun till date. This is 0, so we are here. Proxima Centauri is near. No other star is coming closer. But actually, Proxima Centauri and Alpha Centauri are coming closer. Eventually, at this point, they are falling around 3.2 light years after some 25,000 years. So after 25,000 years from today, both Alpha Centauri and Proxima Centauri will be the nearest star for us at same distance, and then Alpha Centauri will come closer. Proxima Centauri will go away from the Earth in their orbit. They are orbiting, so their distance from the Sun is changing. For few thousand years, Proxima Centauri will be the closest star, and then another star called Ross 248 will come even closer till we are 45,000, and then another star, it will go away from the Sun, but other star Gliese 445 will come eventually around 50,000 years from today. That will also go, and then for another tens of thousands of years, Alpha Centauri will be closest to the Sun. So this shows that basically stars are also moving objects, but their motion takes huge time. We can't say star moving with naked eye in our lifespan. We can observe motion of the star using high-tech telescopes, but not with eyes or with amateur telescopes. We cannot see star moving. But stars are also moving in terms of thousands of years. I'll skip some of the presentations. They are interesting, but I will not move. I will go to the last part of my slide and we'll finish in 5 minutes. All this knowledge we are gaining is very tricky to gain. See, most of the amateur astronomers or laymen realize that if we have a telescope, we can see a star through the telescope. We can see some movie-like thing. We can describe in paper and we have research. People feel that if we have a telescope, we can directly see the stars and processing occurring on that, and we just need to see it and describe it. But no, research is not like that. Like, I'm showing you a real image acquired by a telescope, our own telescope, PRL telescope, situated at Mount Abu. This telescope, using this telescope in infrared colors, I have observed 3 stars. This is the star of my object. You can see a very ordinary dot-like structure, but I later know that this is not a single star, it is binary star. The one star is white dwarf, dying star, dead star, whereas other star is cool star, M-type star. Because of the high gravitation, high mass, the material from this cool star is accreted onto this white dwarf, forms a disk and many other things. We also know that this cool star has spots on their surface like sun and all. How can I know all this information just from this dot? I cannot know. I cannot see this picture. This is artist's impression, my own impression, but not the real picture seen from the telescope. For this, to get this picture, to get this understanding, I need to study this star in great detail. It is highly tedious, rigorous study. We need to observe the light of the star and see the variations in that. We need to take spectra and see the features of this spectra. And we need to understand this data, observational data, using some mathematical models. We need to fit them. We need to apply non-understanding called mathematical model to the observations, and then only we come to know that the stars are like this. So astrophysical research is very tricky. It's very much like detective work. You are given very few things, and from that, from your common sense, from your non-physics, you need to understand the system as a whole. This is my own home facility, my second home, I would say. This is my observatory, the picture of Mount Abu Observatory situated at Guru Shikhar, the highest peak in the Aravalli region. Since this is my second home, I should have a second wife also here, right? And this is my second wife, our own telescope, 1.2 meter class telescope. Why I say it is my second wife? Because I used to visit this observatory twice or thrice every month for 2 to 3 nights. I spend nights with this telescope, and using this telescope, I go out of the world experience, see the stars, observe them, but not always in amateur mode, most of the time in professional way, with rigorous studies, and the prime purpose is to trying to have feel of nature. With this, I'll stop my presentation. Thank you all. Thank you.
So you would have an option of stop share on the top of the screen.
Okay, okay, okay.
Please
So I'll
click on
stop
that
it.
option. Okay.
Okay.
Then
Yeah,
now,
done it.
now we can have 2-3 questions from the participants, and rest of the questions we can take from the feedback form. Right, sir?
Okay. I
Okay.
hope I have not taken not too much of time.
No, no, sir. It is totally fine. We have a question from Tapan Patel.
Okay.
Yes,
Yes.
Tapan.
Hi, Tapan. Yes. So will they write in chat box or?
They are
Thank you,
writing
sir.
in chat box. They will speak as
Okay.
well. Yes, Tapan,
Okay.
you can ask your question.
Yeah. Please unmute your mic and.
Tapan, are we audible? Okay, we can take the next question, sir. We have
Please.
question. We have one question from Dilip A. Parmar.
Yes.
I suppose he has some problem with his audio. We will just move on quickly.
Yeah.
And,
I think moderator has to unmute them.
yes,
order
we
to
are
allow.
unmuting them. We are unmuting
Okay.
them, but there is some technical problem with their end as well. Okay, so we can have a question from the chat box itself, sir.
Yes.
The question is how the age of stars. Just a second, sir.
Yeah.
Okay, so the question is, sir, how can we distinguish whether star will be collapsed after it runs out of fuel or it will go under supernova?
Okay, 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 yes. So it is very interesting to know what will be the fate of the stars. And we have two methods. The first method is the observational methods. If we find some star in the dying phase of their life, we can observe them and see how they are behaving or what are their state now. The other method is the mathematical modeling method. We design a mathematical model, or in other words, a computer program using non-physical principles, physical laws, and let computer to evolve that system. I put a clump of gas with given temperature, densities, and all as a computer model, and then ask computer to evolve that. Then computer will evolve that system in very fast manner, say every few 100,000 million years steps, and then we can quickly see how this clump of gas will evolve. So using these both techniques combined, we know that how these stars will have the dying phase. So if the star has a mass less than some threshold mass, say a few solar mass, then the star will have different kind of dying process. It's different kind of death mechanism called red giant phase. Our sun is less than that threshold limit, so sun will has a red giant phase and eventually it will form a white dwarf. But if star is much massive, more massive in mass, say larger than 2 solar mass, 3 solar mass, or even heavier, then it will go through a process, a violent process called called supernova process, and eventually it will form neutron star or black hole. The supernova process is so violent that the total energy emitted by the supernova in 1 second will surpass the total energy of hundreds of billions of stars in its own host galaxy in that second. So single star will surpass whole galaxy during that period. So supernova is very violent process. Next question, please.
Thank you, sir. We have one more
You can
question.
also mention the name of the.
For sure.
Yeah.
Next question is, are the stars spherical, and why the sun is rotating at different speed at equators and poles? Is asked by Harsh Pratap Singh.
Okay. Yeah. So interesting question, Harsh. You have asked two questions. I request people to ask one question so other will also have opportunity. So most of the stars are spherical in shape, but as I told you, 90% of the stars in the universe are binary. Binary star can be in different separation. Two stars may be very far from each other, or two stars may be very close to each other. If the stars are very far from each other, then they are spherical independently. But if they are very close to each other, the gravitation of one star affects the shape of other stars. Same way, the gravitation of other stars affects the shape of other stars. And so the shape of the stars will no more spherical, but they are very much like water drop shape. So the technical term explains this shape, and the physics behind is called Roche-Lobe geometry. So physics students can study this Roche-Lobe geometry, can search them and can study them. They are very interesting. So yeah, they are not in spherical. The second question was, sorry, I forgot the second question. What was that?
I shall repeat the question.
Yes, I'll just repeat the question. Just a second, sir. Hold on, because there are many questions coming on.
Okay, I think we will move to the second question. Sorry, Harsh, I cannot answer.
No problem,
yeah,
sir.
please.
We can read the question. Why the sun is rotating at different speed at equators and poles?
Yeah. So why the sun is rotating at different rates? The rotation of the sun is, very tricky part in the sense that the sun is actually the ball of fluid, and the differential rotation involves the processes occurring within the structure of the sun. So magnetic field and various currents occurring on the under the sun actually drives its motion. But primarily the rotation comes from the cloud itself, from where sun forms. So this differential rotation, we know partially that it is driven by the inner processes of the sun, but we not yet understood fully. Various questions, including the differential rotation, is not yet fully understood. Next question.
Yes, sir. The next question is, sir, as you said in your second slide, cooler stars are smaller and hotter stars are larger. So how size of a star is depend on the temperature? This question is asked by Vidhi.
Okay. So how the size of the star depends upon the temperature. Actually, I would say the size of the star is not depending on the temperature. Rather, the size and the temperature, both these quantities are depending on mass. Most likely, mass is the primary parameter which drives the stars. So, star forming processes, whether it is cool star formation or hot star formation, is not yet understood fully, even partially. We know partially how the stars are formed, but our understanding is very poor. But primarily, the mass of the chunk of that gas initially, before forming star, drives the shape, the size, and the other processes, the temperature and the other processes of the stars. So mass of the star is the primary parameter with which we can understand this.
Sir, one last question. This question is asked by Himanshu, and his question is, sir, how do stars store energy?
How do stars
store energy?
Store energy. Okay. So the question is interesting. I will say stars are not storing energy, and then I will say stars are storing energy. So first of all, stars are not storing energy. The energy are keep generating from the core. They are keep moving towards the outer surface area, and stars are keep emitting this energy. So it is continuous process. So stars are not storing energy, but at the same time, I will say that stars are actually storing energy. The reason being, the energy are primarily photon, electromagnetic radiation, high energetic. The core is actually producing high energetic gamma ray photons. But these gamma ray photons, high energetic gamma ray photons, are not directly reaching to the surface with the speed of the light.
Special thanks, sir.
Okay. So these photon, gamma ray photons are not directly reaching to the surface and leaving towards outer space. Thank God. If this would be the case, then life could not be possible on the Earth, because the gamma rays from the solar core will kill us before formation of any creature, evolution of any creature. Actually, these gamma rays are moving randomly within the sun and reaches after long path, long drunkard's walk path. जैसे कोई drunkard person पैर इधर इधर करते करते महफिल से अपने घर तक बहुत लंबा टाइम लेके जाता है, वैसे ही फोटोन भी एक लंबा पाथ, लंबा टाइम लेता है, और in this process it will split in 1 to 2, 2 to 4, 4 to 8 and so on, and in that process they will reduce the energy of single photon also. Surprisingly, you will surprised to know that photon will take 5 million years, 50 लाख साल लेता है कोर से सरफेस तक पहुंचने में. सरफेस तक पहुंचने के बाद जस्ट 500 सेकंड में हम तक पहुंच जाता है, 500 सेकंड में. बट कोर से सरफेस तक पहुंचने में वो जो ड्रंकर्ड पाथ है वो 50 लाख साल लेता है. And in that 50 lakh years, it is actually stored within the sun. So if the core of the sun is, go on the strike, and it will say that now no more I will produce energy, still Earth will get continuously getting energy for next 5 million years, because sun has stored such energy. शायद उनको पता होगा कोरोना का फेज आएगा तो उन्होंने भी स्टोर करके रखा है कुछ. Okay. Thank you everybody for listening me patiently. I hope I have come to your expectation.
Yes,
there are
thank you.
More than 130 questions. We will take every question in the Google form. There was one single question asked by more than 35 participants. So I'd just like to read that question. That is, sir, how we can apply for internship at Mount Abu Telescope Observatory, and how we can communicate with the second wife, that is telescope.
Very good.
Very interesting. Yeah, if I would be in the audience some 20 years back, I also would have the same question. And I had this question when I was in my school and college days. So I visited Mount Abu Observatory when I was in standard 12, and I was not allowed to enter that observatory, obviously because of high security concerns and all. So I have taken some pictures from Guru Shikhar temple, and it was my dream those days that I will reach this place sometime. So yes, all of you have the same question. So PRL is running various programs for students. One of the program is called Summer Internship Program. So PRL is announcing every year in the period of January, February, March probably. It is announced in its website. You keep visiting the website, and you can apply online. You can also provide your documents as mentioned in the online form. And then our committee will scrutinize. And then if you get this opportunity to work as an intern in summer workshop, then you can join astronomy division and you are allowed to visit Mount Abu Observatory. This is one path. The other better path is, I would say, finish your MSc. By the time, prepare yourself for competitive exams and interviews. After MSc, apply not only in PRL but in other various institutes in astronomy or in physics in general, and try your hard best to get selected there. If you will crack any of these exams and interview, you are welcome in the field of research.
Yes. Thank you so much, sir, for answering the questions. Sir, before we proceed to vote of thanks, I request Dr. Rajesh here, is the head of the Physics and Electronics Department, to please thank our speaker. Yes, sir.
So wonderful, wonderful. Your talk attracted both amateurs as well as people who are in this field. And such a complex topic, the way you presented, started with the graph and you went into the details. Uh, as a teacher, would like to really appreciate the way you could pack so much of information in this 1.5 hours. Thank you so much for such a wonderful talk. You're going to be really pestered with your really ignited young minds, and I'm sure many of them, as such, astronomy is the most favorite branch of physics which the students are attracted to. And I'm sure many of them are going to go join you as researchers in future. Thank you once again, sir. Thank you so much.
Thank you. Thank you again. Thank you. Thank you.
Yes. We also have one senior most professor along with us, Professor Breach Mohan Thakur from Sardar
Yes.
Patel University. So on behalf of the organizers, we would also like to thank him for being with us today. I now request Suresh Parekh, student of St. Xavier's College and one of the members of the Astronomica Club, to present vote of thanks to our speaker.
Thank
Yes,
you so much, Harshad. Am I audible?
Yes.
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 Okay, good evening, everyone. It's my privilege to offer a vote of thanks of the first session of Vyom webinar on observational and theoretical astronomy. I hope you have enjoyed the session. It was a wonderful and interactive session. I'm a bit confused. How shall I conclude this session? Because for concluding this session, we require another webinar. It was so much informative session. Thank you so much, sir, for such a great informative session. I will be very brief for the conclusion. So we came to know the difference between the astrophysics and astronomy. Then we understood about the HR diagram and its importance in astrophysics. Also, we were introduced to various types of stars and learned about their life cycle from their birth to death. Then we understood about sunspots. Then we experienced aurora. We came to know a lot of information about sun, which we were unaware about. We understood the formation of sunspots, solar corona, their size, and sir is the puzzle for the temperature of corona and solar corona. Then we learned about red dwarfs and brown dwarfs. Sir made us understand complicated theories in such a with some good real life examples. Thank you so much, sir. And at last, you gave such a great life advice for all the young minds. On behalf of Astronomica, Astronomic Club of St. Xavier's College, Ahmedabad, I heartily thank Dr. Vishal Joshi, sir, who has spread his precious time for our webinar. I thank St. Xavier's College, Ahmedabad, our principal, Dr. Father Nancy Lord D. Cruz, our HOD, sir, Dr. Rajesh Iyer, and our mentor and guide, Dr. Tushar Pandya, sir, for giving us guidance 24/7 for making this webinar happen. Also, I would like to thank Physics for Tomorrow Club and members of Essencetech, Mr. Harshal and Mr. Chintan, for their kind support. And the participants of the session, we are overwhelmed by the response and enthusiasm. And last but not the least, the warriors of our Astronomica Club, Jahan, Vaibhav, Bhavya, Kishan, Misil, Kanil Bhai, Yash, and all the supporters who have been working 24/7 for make this webinar happen in such a short time. Thank you all, and we expect you all in tomorrow's session with such great enthusiasm. Thank you all for participating in Vyom.
Thank
That's
you.
all, sir.
Thank you all. Thank you all participants for attending and for appreciating comments on chat. Thank you. Thank you, everyone.
Thank you very much. Thanks a lot. Thanks.
Thank you, sir. Thank you.
Thank you, sir.
Now
Now we can end.
you can leave the meeting. You can leave the meeting now.